Good morning. Thanks for coming to our talk. Let me introduce myself. My name is Caner Balci. I'm from Uber's real-time analytics team. And today I'm joined by Jiali from Uber's machine learning platform. And we would like to talk about real-time ML model monitoring with Datasketches and Pinot, of course. The reason we wanted to present this, we wanted to talk about this is two reasons. First one, this is a pretty cool feature. Datasketches are very cool, and they're relatively less known feature of Pinot. Especially their advanced features are not very well known. And then the second one is the approach here. The application is, again, a novel application, and it offers some advantages compared to the standard ways of doing analytics. So we just wanted to go over those and then share with you. Let me start with the agenda. So in the first part of the talk, I'm gonna try to introduce Datasketches very briefly and show how they are used in Pinot, the advanced features as well. And in the second section, Gia is going to do a deep dive into a real-world application with ML model monitoring. So, and then in the last 5 minutes, we wanted to do Q&A if you had any questions. So let me start with the definitions. What are Datasketches? What is a sketch? So Datasketches are a group of approximation algorithms which provide resource-efficient solutions to some difficult data processing problems. So two things to highlight here. These are approximation algorithms, so that they generate approximate results. If you can accept that, if your use case is able to can use approximation results, you can get a good trade-off in terms of resource efficiency, less resource usage, space, CPU, etc. So just very common examples here. I put distinct counting is the one that is very common. And then the solution for that, one of the solutions at least, is using hyperlog. So why is distinct counting hard? So it's distinct counting. How do you do it in a naive way? Is you maintain a set in memory and then go over all of the items in your collection, and then you add the ones that don't exist there, and then increment a counter, and then return back the result, right? But when the scale gets larger and larger, this becomes intractable, almost like you have to fit the whole set into memory or whatever storage you want to store it to. It can become quite expensive. So hyperlog solves this problem, or like attempts to solve this problem with hashing and then mapping the set into a smaller binary space, and then does some probability calculations to estimate the cardinality of the set. So this is very common, actually, even though you may not be writing hyperlog in your terminal every day. When you do approximate distinct count in most of the SQL engines, it's probably using something like hyperlog or very similar. Similarly, quantiles are difficult for a similar reason, and you can calculate percentiles using more efficiently if you can accept like approximate solutions. Let me go to the next one. So we're going to talk about a specific library today, which is Apache Datasketches. Let me go over the properties or what it is. It's an open source, top-level Apache software foundation project. It has Java, C++, and Python bindings. It's designed for large-scale data processing. What this means is it enables distributed computing. Sometimes these libraries are not designed for that, but in this case it is. And it is supported in PostgreSQL, Druid. You can use it with Hive, and then now also in Pinot with the additions in the last years or so. So what sketch families does it support? It supports distinct counting, like the example we gave. It has multiple implementations for that. There are quantile calculation functions, a group of functions for calculating the frequent items in a collection, like called heavy hitters, and also some sampling. So okay, what do we have in Pinot? Pinot has a bunch of these functions built in. You don't have to use a module or like an extension. They already exist if you have a Pinot deployment, maybe due to version 1 or 2 may be missing. But most of them, for cardinality estimation, we have distinct count theta sketch, CPC sketch, tuple sketches, which is an extension of distinct count theta sketch. We have a percentile KLL function used for estimating the percentiles, and then 2 sketch functions for doing frequent item analysis. There are also other sketch functions in Pinot, not from Apache Datasketches library, but I won't cover them in this talk, but you will see, for example, ultralog-log, hyperlog-log are from different libraries. So what do we mean by Pinot supports these? Just this is a simple example. You can see we can do a distinct count using this distinct count theta sketch function. You pass the column you would like to estimate the cardinality with, and then it takes some parameters. In this example, I put nominal entries 1, 0, 2, 4. You can use group by, order by with these functions, just with any aggregation function. One thing to note here, the nominal entries, something about the data sketches. I'm giving this configuration to configure the size of the sketch object itself. So this is about a trade-off you do. You can have larger sketches, which are more accurate, but you can have smaller ones, which give more errors, have larger error bounds. But this trade-off is available to the user in case you want to get it smaller or faster, etc. So this is the case with Pinot as well. Another example that's a bit more advanced, I call it level 2 integration. The first one was just merely using the sketch algorithm internally inside Pinot, but this example uses something else. So these functions have row variants, which return the sketch object to the user. It's not just calculating a percentile for a data set, but it's returning you the whole binary object in case you want to do further processing. So in this case, you see percentile row KLL, and then we are passing the delay minutes column. It returns a sketch in a base 64 encoded form. So in the bottom, you see how we can use this binary object to recreate the sketch. So we use the Datasketches library to wrap it with this KLL double sketch constructor, and then we can print out mean, median, max values. This is useful because there are more to these sketches than simply calculating min, max, median. For example, you can get CDF, a cumulative distribution, or probability mass functions as well. In case you want to do further processing, these are available as well. So I would like to also show Pinot aggregation framework a little bit to make the picture more concrete in your mind. There are a lot of things in this diagram, but almost everything is the same. I want to show it to you. So on the left, you'll see 2 Pinot servers. In the middle, you see a Pinot broker, and all the way to the right is a response. So you can think the data is flowing from left to right. This is as the computation is done. So imagine there are 2 Pinot servers. We have a distributed computation going on. All the way to the right, you have raw data, the segment. And when you run an aggregation, any kind of aggregation, sum, mean, median, max. So these aggregation objects are created per segment, even lower than the segment level. But for this purpose, they are created initially inside the server, and then they are merged inside the server, and then they are passed to the broker. They are merged further. So what I'm trying to show here is this computation graph is like a tree, and this computation fits nicely with the way these sketch objects work. So when you do aggregation using sketch objects, these aggregation objects actually wrap those sketches. And then you can think those sketches being passed around, getting merged. They go through network boundaries, etc. So when you want to do optimization with them, this is the picture to have in mind. And then with this in mind, I would like to also show another example that I call this a level 3 example. This is more advanced. So in this case, in the previous case, we were using the raw data to calculate sketches and then return a response to the user or the query. But in this case, what we are doing is, the first code example is in Java. So you can create the sketch object externally in some application, maybe a Spark, maybe a Python application. And in this example, you can see this sketch is representing potentially millions of rows of data, right? You're digesting some data into a single record as a sketch object, and then you can ingest it into Pinot, either through Kafka or offline batch ingestion, stream or batch ingestion. And in the end, very similarly, you use the same sketch functions to use these sketches. When you run a sketch function, if there is a binary object, Pinot attempts to deserialize that into a sketch and then utilize it as if it was like raw data. So here, the thing I would like to touch the implication here is with this approach, you can reduce the size of raw data in Pinot substantially. You don't have to store raw data. You can have a digest snapshot. Maybe you can have them with certain dimensions. And inside Pinot, you can arbitrarily choose any subset and then merge them on the go. So you have a sort of summarized representation, but not really mere summarization because it can be mergeable, a mergeable summarization of your data. So here's a picture of one example. So you can have Pinot as a sketch store where you generate sketches per date string and then write into Pinot for each date string a single sketch. So Pinot only holds these sketch objects, and it can do merges and answer arbitrary queries for you. It can even return merged sketches to the user to do further processing as well. So with this in mind, yeah, this is big compression, big compression of data. So I would like to leave the floor to Gia at this point to show you the use case, how we utilize this at Uber to solve the ML monitoring problem. Yeah, thank you.
Thank you, Jenna, for the intro of the Datasketch and also its integration with Pinot. So now I'm going to walk you through how we are using it for ML monitoring solutions. To give some background, so I'm from the Uber ML platform team. So we are trying to build a solution where, so on the platform, we're serving a lot of models for all different Uber use cases, like fraud detection, ETA prediction, etc. So for those use cases, there's a common need. They want to monitor their model qualities. So we are trying to build a generic solution for different use cases, so they can all using this one to monitor their data quality, model quality when they are doing machine learning solutions. Now, I will walk you through, this is the agenda for this one. I will first talk about what's the challenges in ML model monitoring, and also what is ML lifecycle, etc. After that, I'm going to answer to that challenge with these data profiling and sketch store solutions, where we can build these generic monitoring solutions. So first slide is this one. This one is just to give everyone a background on what's the typical ML workflow. I think this generically applies to most of the people doing machine learning solutions. So let's take a look step by step. The step one is you first you need to thinking of what's the problem you are trying to solve. Maybe you are trying to predict the housing price or trying to predict something else. So when you like a problem defined for your thing, then you start looking at in your company what data do you have. The first step is data ETL. Maybe for the housing problem, you want to aggregate the housing price every year and also for all the zip codes, etc. So you need to do some data preparation. That's the data ETL. You convert from the raw data into the data that's more favorable to train machine learning models. Then the second step is the feature engineering. That's why it's very connected to data ETL. In that place is you need to define, I need to train maybe using 3 years data or how many years data. Then how many tables I need to using when I train my models, etc. Then you also do some feature transformations, etc. Then after those steps, then you are going to having training data after step 2. In step 3, you will start thinking, I need to define my model structures. I can use some TensorFlow models, PyTorch models, or tree-based models to see what's the best structure, what's the hyperparameter I should use to tackle this machine learning problem. After that step 3, you have a model. You train with the training data. Now the step is you need to evaluate the model. So before you use it in production, you need to tell how good is the model. By doing that one is basically you having some new data which you never used in training. We call it evaluation data. It's coming from probably the same pipeline, just maybe a data string cut off, etc. Then you have the evaluation data run through your model to see for your prediction and also the actual the ground truth. What's the accuracy is? Are you predicting the right price? Then after that one, you kind of satisfies your model performance. Next step, you need to push the model into either online inferencing or offline inferencing. That's mostly dependent on the use case. So in online inferencing, the client will send a request directly to your service. Then you run the model, then return back the response. In offline, you just run a batch workload through all the offline data. I need to run maybe send a promotion on weekly. Then I just run that one weekly. Then I get the results there. So that's the machine learning model lifecycle. Something I want to highlight here, you see all the green box. All those green box is the topic we are having today. So inside the machine learning lifecycle, there are really a lot of data sets, and they also living in different runtimes. They could be like a hive table in data warehouse. They could be the inference log in Kafka, or like just maybe some real-time stores like Cassandra where you fetch the data. So the data really live in all the different places. They live in different storage. We need to do monitors on those data. So that's our problem we are trying to solve here. So to more emphasizing on the what's the problem we are having here. So we say we are trying to monitor the models and also the data, but what are we really monitoring? What's the problem of the data quality problem here? So ML, if people summarize in really simple, is data plus code. Basically, you prepare some data, then you define your model architecture with the code, then you start having a model. Later, you also feed in new data, you get a prediction. So it's really data plus code. Code is you define the model architecture section. Then there's these few scenarios as the machine learning engineer they will be facing in their daily development. First, before I train the model, I see I have all these numbers of data in my data warehousing. Which one I should be using? Maybe there are some duplication, or there are some before I using it, I need to know what's the quality of the data, whether it's fit my assumption for the data distribution, etc. The second question is, I train a model, but somehow my model performance is bad. So I realize my prediction is way off than the actual price. Then the next question people need to answer is that because I choose the wrong model architecture, or is it because the data itself having the quality problem? So you are trying to rely on some features, but those data quality is bad. Then the third question is, after you push the model into production, the model can still, it's already running there maybe for a few weeks, but suddenly the model performance degrade, then what is causing that one? So those outage mitigation, root causing problems. So those are the things. Here are the impact. So if the training data is bad, then it leads to bad model quality. Then all the expensive GPU resources we have wasted for those training. And then the second one is you have to have a model, you are evaluating the model. If the evaluation data set is bad, then it's leading to arbitrary model performance results. Then your decision-making process is like broken. So you cannot make a reliable decision after evaluation. The third one is really, after I push the model to production, I see online data is having trouble. Then it directly impacts my business. So to summarize the challenge here, first we have many of data sources. For example, at Uber, we have Hive for the training data, etc., and we have Kafka. And also we have a lot of informal data. They never be materialized in any place, but actually I just join them on the fly and use those for training evaluation. So those data, they are not materialized, but they are very critical to my model performance. So I have these different data sources. And also I have a scale challenge. To really make a deep learning model perform, you actually need to feed into a lot of data for training. So whenever we want to monitor those data, I also need to handle the large data volume problem. And also a large number of use cases. As mentioned, we are trying to solving this problem generically for different machine learning use cases across Uber. So there's a lot of use cases. What I mean by that is some people, they want to monitor maybe regional-wise. Some people want to monitor the data maybe like time-wise. So basically, people have different segmentation requirement also. That's coming to play. The third one is more unique to machine learning. The third challenge is the different expectation for different columns. So what I mean by that is so let's say I'm trying to using the data for housing price of per zip code. That's one of my feature. But thinking you have hundreds of engineers working on all different problems, it's kind of unrealistic for asking your engineer or data scientist to define your expectations, to say, what should be my data looks like? What should be the missing rate? What should be the distribution looks like? You can basically, they can give you some very simple one. They should never be negative, etc. They should never be some very high bound. But really between those, there are still a lot of places you can get it wrong. How you can getting the expectation, letting user describe the expectation. So that's the third problem. So with that, without further ado, I will go to the solution. So we do the solution, which is the sketch-based solution. So basically, we are trying to do a summary or do a monitoring on the data, all the data flowing in a machine learning system. So with this solution, what we call this like bullet points. Then the first thing is like we want to achieve the goal because we have all this large data set. We don't want to every time when people investigate or query, we issue another query on the raw data. That will be very expensive. The best we want to do is like we only scan the data once. We don't want to visit the data more times for different type of alerting or debugging queries. The second one is we create those mergeable column level data profile. Thinking you are dealing with a tabular data, then for each column, we are creating those mergeable. Why mergeable is important is because people having different requirement for segmentations. So one engineer comes, they want to merge, they want to see like divided by every day, every hour. The other engineer comes, they want to say regional, etc. We can collect some basic requirement, the finest granularity we want to offering from this big data sets. Then we just calculate for each cube, for each granularity. Then we calculate those data sketch. Data sketch is very small in size, so it's really still making the data, like you can feel like a compression or summary. It's making the data very small. Then after we calculating, we have Kafka, ML workflow, we calculate their data profiles. Then we push all their data profile into a centralized store powered by Pinot. Then after that one, we can do query and cross-validation between different data. I have a slide later on to really explain what I mean by cross-validation. That's very critical for machine learning model monitoring. So this is just to reiterate on the what Jenner already showed on the graph. So in this graph is thinking the real example. So we have our Hive table or maybe streaming data, etc. So every data string that's like the newly generated data, we run a job. The job will scan the data once, generating data sketches for each columns in your table. And also based on the segmentation configuration, we can also generate sketch for those segmentations. So after we having the sketch, we store those in Pinot. Then the Pinot also support inline merge. This one is really, I think is very important for our use case and also for other people, I feel. So at the beginning, before Pinot support this data sketch, we also using some storage like Pinot to store data sketch. But what we need to do is we need to fetch all the, like use it as a key value store. We fetch all the things out, then merging in our service code. That one making things really slow. Then with Jenner team help, then we are able to pushing the merging logic into the Pinot storage. So Pinot can directly merging with the aggregated object, those things to merge in line. So that's really saving us 1 to 2 magnitude of the time latency. So with that one, it can really unblocking, like you can thinking like a dashboarding experience. People just open the UI, select the data sets, the dimension, they immediately see within a few seconds, they see all the data distribution, etc. They can see that one. So that's our use case unblocked. Then after we having this merged data sketch, then it's coming to the metrics. So I keep talking about monitoring. What are we really monitoring? So monitoring means for the data, some basic things like null percentage, percentiles, or I show you a histogram, so people can resonate whether the histogram makes sense. And also we use other metrics like KL divergence, Western distance, a bunch of statistical distribution measurement. Basically trying to measure two distributions, whether they are similar. So in our example here, you can see for the recent data, we compute a mergeable data sketch, maybe recent 1 week data or 1 day's data. Then for last month, I also compute another merged data sketch. You can think the data sketch represent the histogram. Then I put those two histograms side by side. I can run those calculations to tell you how different are the histogram. I have then I normalize the distance to 0 to 1. Then people get a sense like whether the data really change a lot across time. So this is the same data set, but across time, whether there's any data drift or data quality problems. So that's the problem we are detecting. And then that's a logical solution. Now I'm coming to my physical architecture actually. So when I lay out this one, it's kind of reiterate, but just to give you more concrete ideas. So we have the Kafka data, data warehousing, Hive data, machine learning workload is just the informal data. They never materialize anywhere. So all those data, on the left side, we first call it data profile producer. Then we have different jobs, maybe Flink job for Kafka and a Spark job for Hive, etc. And also for ML workload, we have some inline provider. They are very lightweight, just scan the data once, converting data to profile, sketch-based profile, storing Pinot. Then we do the profile query engine, which is a service which can understand the sketch, convert sketch to either the percentiles or to KL divergence. So it's all happening in this service. So then after that one, we open the gate. People can either do alerting or do dashboarding. So all those things are becoming very lightweight. So one thing I want to, there are some benefits I already talked about. One is the definitely reduce the data size we are dealing with. So from the petabytes data, very useful training, serving, etc., all those logs, then we compress them to really smaller size with the profiling process, then storing Pinot. Then all the further queries, dashboarding, alerting, they only need to deal with these small data sets As one thing is can save cost. The second thing is can be real time. So thinking you are debugging an outage, running the queries on the raw data, it may take a lot of time. But you just have a dashboard, you just click the button, then you immediately see the metrics, see the distribution. That's really making the life much easier. Also, you don't need to write the whole queries. That's one itself is also error prone. So we have this thing supported. The second thing is we enable the cross validation. So that's back to my challenge I mentioned for machine learning data. How you define the data expectation. So I cannot ask a user to give me a histogram expectation for every columns, but in machine learning, but we have the same data. For example, the average housing price for zip code. So the same data will exist in data warehouse, in my ML workload, in my Kafka data. And also it will also appear over time. So I recompute this data maybe over time. So we're using the consistency to solving this accuracy problem. So it's not a perfect solution, but that's helping us. So I want to check this Kafka data, whether the online Kafka data is correct. Without having the expectation, I can cross-reference with my training data, or with my Hive table data, or just with my last month's data in Kafka. So with those signals, I can tell whether data is really different between the Kafka and the history, or between other solutions. So with that things, we don't need to ask everyone to set up expectation. We can give them these signals. So also the training, there's a problem in machine learning. It's called training serving skill. Basically, when you train the model, you have a set of data. When you're serving the model, the data distribution change, then the model is not performing that well. So with this cross comparison, we can solving the problem of the training serving skills, etc. Yes, I think that's for these slides. So next is just a few links. There are some links we have here. I think it's the second one. So we have this integration inside Datasketch. So this is a Datasketch website, the Apache project. Then we enable the Apache Pinot integration. So you can also leverage the same architecture to solve your problem. So maybe you're not working on ML background, but this really is kind of a data observability problem. So as long as you deal with a lot of data sets in your work, you want to build some observability on it. So this is one way you can really compress your data into a much smaller summary. Then building your monitoring solutions or debugging solution on top of the summary. So it's also also giving back a story. So before we using this architecture, I also built one generation before for machine learning model monitoring, just for online. That's the most critical path. So what we do is we spin up a Flink job. The Flink job just analyzing the Kafka data. Then we calculate the metrics with the Flink job. Then we directly monitoring that one. Then after that one, people start asking how I can cross-compare with other data. And also they're asking, can you provide a similar solution for my Hive data, for my machine learning workload data? Then I either build duplicate solutions, but still I cannot cross-compare them. So with this kind of architecture, one thing is all the dashboarding, alerting, query engine that are shared with different data sources. So you don't need to rebuild all those metrics again and again. And they are very consistent. The same metric you see for Kafka, it will appear for Hive table. And also they can really cross-compare the data source. So that's the presentation I have. I think I clicked the link here. The last slide is just the question answering. So I cannot bring back that slide, but feel free to ask any questions.
Folks, if you have any questions, raise your hands and I will bring the microphone to you. Okay, I'm coming in over there.
Okay, hello. Thank you for the presentation. It's wonderful, and I learned a lot. My question is, when you build those sketches, normally how many number of raw events do you aggregate them together to produce one sketch?
Okay, that's a very good question. So basically, how many raw rows like I'm processing? I think it really depends. So the sketch for training, or Hive table, we really processing a lot of rows, hundreds of millions of rows, or even bigger numbers, then compressing that one into sketch. Then for online one, it's becoming much lesser because we shrinking our time window to be much smaller. We want faster detection. The real-time part come into play. So we want to detect the issue quicker. Then the sketch, then the data, raw data volume is much smaller. But one nice thing about the data sketch is the sketch size doesn't really grow with your raw data size. After it's growing to some extent, it will like flatten that place. So let's say you keep increasing your raw data from millions to billions, your sketch is still relatively like a few kilobytes. It won't really grow with the raw data. Yeah.
Folks, if you have any, okay, Robert.
Thank you, Victor. Two questions. Do the sketches introduce or impact any of the query latency?
Can you repeat, sir?
The query latency, while you're querying using a sketch, does it improve or negatively impact query latency because the sketch?
So this system we built like you can thinking next to the raw data. People can still go to raw data if they really want to dig into. This is like another solution. So raw data, they run a queries, but here it's much faster because we are dealing with a very smaller data sets. So I don't have a good comparison on that one, but the experience we are offering here is a few seconds, then you see the results maybe across days, months. It doesn't really matter. It's just merging the sketch in Pinot and showing the distribution results.
How much accuracy loss have you observed with the sketches?
Yeah, that's a very good question. So there's a trade-off between accuracy and space. So they are documenting in the Datasketch website here. So typically what we choose for our use case, model monitoring, we choose the errors around below 1%. So let me open this one here. So they have a good table here. KL, sketch, accuracy, and size. So we choose this one, K equal to 400 for our things. Basically, 400, this 0.6 means if you're asking P50, I think the error will be P50.68 and the P49 something. Like whenever you're asking the percentile, asking something, the result will be approximation around that one. The error is around, so it won't go to P51 value, the actual value. It will be 50.68, etc. So that's the error bound.
Other questions?
Hey, thanks for the nice presentation. So from I understood, when you do anomaly detection, there is a kind of sketch based on historical data and a new sketch from recent data. And so how do you manage when some sketches in historical data are not relevant anymore because there was a, I don't know, distribution change? Or if there was an anomaly in the historical data, and so somehow you need to remove some sketches to have a correct distribution estimation?
Removing the sketch, I didn't get that part. So why I need to remove the sketch?
Yeah, so you're somehow monitoring anomalies. So at some point, maybe you may have bad data in the historical data.
Oh.
How do you remove bad data, let's say?
Oh, I see, I see. So I think that's the backfill problem. That's especially a problem for our data warehouse. Is that correct? So there's a corrupted data. Then later on, they fix the data. But my sketch is never updated. So I still providing the old data. So is that the problem you are describing?
Yes.
Yeah, for that one, we basically do the backfilling also on our sketch. So this monitoring job need to, whenever there's a backfill event happening for the Hive table, then we also trigger a backfill for the sketch to give you updated view. Otherwise, you see what you see in the raw data is different than what you see in the these monitoring solutions. But for the other data, they are more like a snapshot. They are more immutable because they are prediction logs or the training data. They never change, so they don't have this problem. But for data warehouse, we do have this problem.
Any other questions? Okay, coming in.
So what is the size of the data you're ingesting in a day or hour, however you want to put it, and what is your cluster size in terms of CPUs, cores? How do you run this? What is your cluster size?
You mean the sketch store size? Yeah, right now we are still very small. I think a few terabytes data in our sketch store.
And what about number of cores? Like, how beefy the computers that run this?
The number of cores, our query actually not a lot of queries. So for our things, we basically serving the one is the alerting, the other one is the dashboarding. Our course is not really occupied. It's mainly still the data itself.
What's the number of nodes, brokers, servers?
The number of nodes, I think we are operating on 4 nodes per zone.
I saw someone was raising a hand over here, and I'm coming in and trying to fill the awkward silence with just rumbling and stuff. And here we are.
Hi.
I got it. I got it.
Yeah. This is regarding the use cases. Can you please talk about which use cases that you have implemented this particular solution? And what are the other use cases that could be helpful in kind of, so Uber in this transportation business. So in which industry that this could be very useful?
So what other use cases? So right now, this solution, we just offer generally for all the machine learning solutions. So whoever do machine learning using tabular data, we cannot tackle like image data or text data, which is also very popular right now. So for all the tabular data do machine learning, we offer these solutions. Outside machine learning, we haven't used it yet. Are you asking inside machine learning? We have like really a long list solutions at Uber, close to a few hundreds different use cases. They use machine learning. They can all benefit from this solution.
And we have a time for one last question, folks.
Will the data sketches also be useful for estimating counts as well? And if so, if there are any use cases that you have seen where this being useful for that?
Benefiting for, I didn't get the word.
Estimation for counting of events or counting stuff.
Segments and stuff like that.
Estimation for counting.
Yeah.
Yeah, the data sketch has a, I think in the sketch family they do support counting, but in our use case we don't really use those things. We mainly care about the distribution part. But from the sketch family, I remember I've seen those here. There's this king count. We care about the frequent count where we can capture the histogram of the data. We mainly use these three actually. Distinctive counting, like the cardinalities, the frequent one, where we are trying to capture for For categorical value, what's the histogram? Then for the numerical value, what's the histogram? We're using it to capture those things. For the counting, I don't know.